or designers at some point come across that question from the owner. So this will cover, I think, enough to give you more questions and give you more interest into this whole installation. So today, the way we're presenting it, we have a AIA approved presentation, which you will know how it's progressing by the little logo popping up at the bottom of the slides. So when you have a Rockfon logo or a Bibliothèque logo, you know that we have more specific documents that are more pertaining to company, and AIA allows that format with, in addition, a group of neutral slides. So then you will have no logo whatsoever on those slides. So that gives us a chance to introduce a company, get into the meat of things, and then wrap up with some product offering. There will be some slides from Bibliothèque because I wanted just to add a few things. Him and I have worked on this presentation and produced it a few years ago, and we presented it as well. So I thought it was only fair that he would have his 15 minutes of fame.
Well,
so
thank you.
So here you go. So the presentation should be all in all 60 minutes. If we run a little short, that's fine. If we have more than 15 minutes for questions, that's even better. So here we go.
All right.
So as a company, some of you may recall Roxol back in the days. We have reclaimed back the name Rockwool in 2018. And under Rockwool, you have the entire global company that is around the globe producing essentially a stone wool fiber, and has many manufacturing facilities and salespeople, like technical group in Europe, in North America. And we cover basically just about every country in terms of sales and technical applications. As a company that is manufacturing products out of an inert product, that is the stone that we dig into from the ground, we had to look into some sustainability and what is it that we produce, provide, what are the goals you would like to achieve. And looking at the United Nations 17 goals was a good way to start contemplating where is it that we're good at, where is it we could do some good, where is it we could improve. So what we have highlighted on this slide are 10 of the 17 goals, which make more sense for what we do. And there's an annual sustainability report that exists. And it is available if anybody is interested in reading the accomplishments of the company over the last few years. Insulation side-wise, part and parcel, and I would say the biggest division of the company under Rockwool, you have anything related to insulation. So you have your what we call technical insulation, which is the pipe and tank, the marine industry, the cruise ships, the offshore drilling. This requires specific types of insulation. Oh, somebody... do you say I do not see the slides?
Matthew, you're not able to see the slides?
Maybe there's a delay?
Perhaps.
Oh, he's typing. Hang on. Okay, Chris says he can see the slides. Okay. Okay, so maybe it's something, Matthew, with your computer.
Maybe,
I'm
Matthew,
not too sure.
Could you try to maybe exit and try to join again? Yeah, it might be a browser issue.
Yeah, I will continue, and then hopefully you're able to see them. So the technical insulation, the fire-safe insulation, which is also for all your wall systems, and then what we call core solutions, which are the customized type of products that may need to be addressed. This is the core of the Rockwool group around the world, in Canada, in the States, and in Europe for sure. Are you able to click next? Okay.
Yep.
And then you have the other division. So Lapinus, which is that specialty fibers that would be, for instance, for trains, brakes, for water management. So again, a fiber that is treated and built into extensive filtration systems. You have Groden, which is the greenhouse specialty fiber. So doing a little mold for growing and starting up some greenhouse plants. This is a very, very big side of the business now. It's grown over the years, and essentially just because on Earth there's a need and a very active industry into greenhouse or horticultural businesses. Rock panel is in Europe only. It's a cladding system. I'd be very happy to see that coming to Canada and the States, but there's
Made out
extensive
of stone wool?
everything made out of stone wool. Yes, so cladding systems
Interesting.
made out of stone wool. It's something that is in need of additional testing for the building codes and the markets that we have here that are different than Europe, but it's a very strong business proposition in Europe, very big in the UK. And then my screen hides a little last one. Let's see if I can move that little box and move just. I see Rockfon to the right. So this is us, the baby division. And we are closing on 60 years of business. And it's anything and everything about acoustic ceilings. And that includes the seismic aspect of the installation. Next. Very quickly, the only thing to retain in the slide is that stone wool fiber is very efficient fiber. So with 35 cubic feet of fiber, we're able to produce almost 24,000 square feet of ceiling tiles. So that's almost equivalent of 30 classrooms. So it's like it says at the top, it's a little fiber that goes a long way. And that is, again, the core of the business, whether you apply it to a bed of insulation or ceiling tile. Okay. It's a chart that kind of gives you a sense of where companies sometimes have these hooks. They have synergies. It's a natural connection. So you have Chicago Metallic that has been in the world for a long time, creating suspension systems that started connecting to rock wool, the Rockfon division, and in Europe was from an early stage the suspension system for that acoustical ceiling tile. And in North America, in Canada, Chicago Metallic was known for the suspension system. It was installed with other companies' acoustical ceiling tile. Chicago Metallic had some oddballs in terms of acoustical ceiling tiles, were not mainstream. But eventually, over time, with the evolution of the stone wool market in Canada, so that's rock soul coming to Milton, Ontario, and spreading its wings, there was at some point the official connection of the Rockfon division acquiring Chicago Metallic in 2014. So now we have the official combination of these two items that are necessary to one another, the tile and the suspension. Okay, I have a question. I don't know if I can minimize the screen where I see you without killing anything.
No, I think you should be okay.
Okay, how do I do that? With the little...
just grab it. There's a little arrow on the side.
Yeah, this here. Okay. Oh, okay. Perfect. Thank you. So because the Chicago Metallic company had already have an existing presence in Chicago, the Rockfon business decided to make Chicago the head office. So that means that warehousing, manufacturing of ceiling tiles, distribution, all the support that you think of marketing and so forth is based in the States. But for Canada, that means that we have a very good route truck and full truckload delivery system in place to cover every part of Canada. And as mentioned earlier, it is an AIA approved presentation. So we went through different connections with Green Building, the interior designers, and different architectural associations. So your need for some certificates after the presentation, just send a note to Just or myself. And
you don't actually need to send me a note. I have a record of everybody that attended, so we will automatically send you your certificates. The only thing is just give it a little bit of time because we have to get them from, we have to
from Rockfon.
Exactly.
So see, he's already a step ahead, that guy.
So it won't be automatic, but yes,
very quickly.
Everybody will get the certificate.
Yes. Okay, next one.
Okay.
And
Let's start.
And this is a presentation with copyrights, which means you're not allowed to just go ahead and use up whatever you want. However, if you ask for permission, you shall be granted permission. How's that? All right, let's go into the meat of things. So as you can see now, we will be losing little logos at the bottom. So we get into the official neutral presentation portion of today's seismic presentation. So let's talk about seismic activity. We just saw on the news recently how a volcano is acting up a little bit in La Palma, in the Canary Island. We saw that there have been activity a little bit here and there around the world. Basically, whether it is a volcano or it is an earthquake, you have below us in the core of the earth magma that pushes pressures, and you have at the crust level of the earth, you have these blocks, these plates that basically are cracks that happen over time, and there are pressure that you can imagine in your mind as maybe like a rubber band that you're stretching, and eventually that energy has to release itself back, and the plates and the blocks have to kind of try to get back into place, and the energy has to disperse. So when you have this happening at the fault line, you have all of a sudden a seismic wave, which means that you have an energy that's got to go somewhere. So that means it's going to be an earthquake of some sorts. It could be the magma pushing through a volcano and having a need to get out. So there are cycles to this in some areas more than others. I know that when I visited Iceland a couple of years ago, they were telling us that they were overdue for the big one. So they know that they will have a big eruption with one of their more active volcanoes. And it's just a question of a short time before it really happens. But we are, all connected now by television, by internet, by, YouTube. So we see that there is activity out there. This is the basic of it. This is what's happening when we see these big shows of Mother Nature. There's been a need to, if you will, gather that information to know what goes on. Maybe not to predict things, but to have a better understanding of what is happening in terms of the earth moving and shaking and things changing. So back into, I believe it was in the 1870s, 1879, from my notes, the new government in the United States created the U.S. Geological Survey to try to track these things. So today it is a very, very high level organization. Their website is amazing. You could click on it anytime and see at any time of day, within 10 minutes, where was the latest earthquake or volcano activity. It is quite impressive, and it really, really helps, I think, a lot of people figuring out what's going on out there without predicting, but at least being a bit closer to reality. Next. So the Canadians do a similar kind of work. This, on our side, was organized it was around the 1800s, and it was actually McGill University that started this with 3 machines installed across the country. And they are gathering information. And they're trying as well with the U.S. Their U.S. counterparts to figure out what is going on to better address construction through building codes. So the American side of the map, and we'll have the Canadian map in a second, shows a little bit where, yes, we know that there is activity. We know the West Coast, part of the Pacific Ring, is active, but that translates into other, into the East Coast as well. I was looking for a word here that doesn't come to mind. So you have activities that is on the outskirt, if you will, of the mainland. So it goes all the way to Alaska. It goes into Hawaii. We know that we have volcano activity that's been talked about in the news recently. You have the islands down going all the way down to Puerto Rico, U.S. Virgin Islands that are part of the States, also having activity, and where sometimes we don't realize that the cause of some earthquakes are more central to the land in the United States. So, for instance, in the Atlanta area, there are some ground conditions that are sandy, that are weak, that are prone to a lot more activities, earthquake and seismic activity that we usually hear about. And the other thing that happens towards the Oklahoma City and west of Nashville is that you have underground fracking for oil and gas activity. And that is now what we call a human-caused earthquake. So it's an artificial earthquake. It's not Mother Nature doing it. It's us causing it because we're displacing huge amount of gas and liquids with an air pressure, and we are shifting the solidity of these grounds, if you will, and creating some tremors. So this is something that's quite serious, and it's being addressed more and more because the exploration of natural resources is maybe good for the market, but it's creating something with very strong consequences. Next. So about the same thing is happening in Canada. So the West Coast is very active, obviously. And then as you could see into the north and the Arctic, there's this line that is the outline of the country, if you will, where you have these shifts and these tectonic plates that are moving with some activities. There's less population, so we are not as aware of it, but it's happening. And then if you go to the East Coast, you have stronger red lines, as indicated with the cursor by Juste, where is the St. Lawrence River and the Ottawa Valley. So there's a fault line under the St. Lawrence River. So we do have quite a few earthquake and tremors on different level. And again, that fracking was something that was discussed a few years back. Apparently, there's a possibility in the Gulf of the St. Lawrence River to go and access some natural resources, some gas and some oil. And there was that discussion about maybe using fracking as a method to recover these materials. And then the discussion kind of died because everybody red flagged that fault line, saying that might be not a good idea to do that. So I'm sure we'll come back again just because now the price of oil is up. So people will say, hey, there's money to do. You never know. So what happens to those buildings when the earth is shaking? Next. Okay, so first of all, there's a loss, is a loss in terms of goods, of assets. It's not just the building, but it's what's inside that's demolished or damaged beyond recovery. So there's a cost associated to that. As you can see on the slide, $6 billion annually is caused of losses is caused because of the earth shaking. So it's not like the buildings are going to collapse on your head, but there's enough tremor and moving to create serious damage. So it's not just us. It's not just the Geological Survey that is association that's looking into it. It's insurance companies. It's money. You can split this attention into specific things. It's either the structural components or it's what you call the non-structural components that would be affected. So it's about the 25-75 break. So on the structural side, we're talking the actual concrete, steel, wood structure that could be damaged beyond repair. On the non-structural side, it's everything that's inside. So it could be not very important to most people because it would be, let's say, an office furniture. But think about your big data centers. Think about museums, collections that are valuable in the eye of the humans because of their rare items, the history they convey. If these things are demolished because things are shaken and broken, or because the shaking has ruptured a gas line and now you have a fire, you have things that are priceless that are lost. So that's where, all that, the reckoning of all this comes from, and that's where it's going, trying to prevent all the damage.
Yeah, and it's interesting to see that that accounts for about 75% of like, the building cost, right? So we always think that
It's huge.
if we don't lose the building, we're okay. But like, what's inside is just as valuable or even more valuable. So
Yeah, yeah.
yeah.
So you have a lot of people that said, well, at some point, okay, that's fine, it's happening, we have to live with it. What can we do to prevent that damage? So building codes started to establish that connection, saying, what is it that we could do in terms of building designs? So the IBC, which is the American code called International Building Code, started to add on into their documentation in the 50s what could be done in terms of prevention, better building designs with specific seismic documentation and standards. So it's about every 3 years that this gets to be looked at and reviewed, and different agencies will contribute to that. And the Canadian side of things, we will see a little bit later, does a similar amount of work. So what do we do with this? Well, what we do is that we try to create ceilings that will stay in place as long as possible. The idea, again, is that it's not that the ceiling is the most heavy thing to fall down, but it will create damage. It will also create, maybe in a moment that it's happening, a blockage before right before a door that is your exit, your egress. So we're talking about this here today in a very cruel manner, but when this happens, I'm sure that we don't think necessarily, we react more. So a door blocked by a bunch of ceiling tile could all of a sudden look a catastrophe. I cannot get out, as opposed to thinking with a cold head, that you could move things
Just
around,
walk over it.
or walk
Yeah.
over it.
Yeah.
But again, if it's the ceiling tile that falls, or it's the entire grid system that falls, there will be something there. And it's probably the first thing to fall compared to the rest. So that's where, at the end of the day, for ceilings, it became more important to consider what could be done to prevent and mitigate that failure.
And potentially the ceiling mounted equipment too, right? So any light fixtures or to keep
Exactly. Yeah, all that was looked at.
yeah.
So this is the American procedures for evaluating what needs to be done and adapted and adjusted and added to a building code. So you have those agencies, the International Code Council, you have the Society of Civil Engineers that create a lot of documentation and analysis. You have also the American standards, and they all produce documentation, and eventually they make their way in terms of integrating these additional documents into a building code. So the building code supersedes the next version and the next version, but with these additional documents. So the civil engineers have and do a lot of work in that regard, and then the standards, I would say, create a consensus in terms of what is best to be addressed, because you have to think again from coast to coast what is the best in that function.
So yeah, so this is like a similar thing also happens for Canada. Sorry about the question mark. So you would notice that there are some bibliothèque slides, and that just indicates to me that I have kind of like supplemented Isabel's presentation because when we started talking about it, I said, hey, your presentation needs to have some Canadian content because we have a lot of people joining us from Canada. So very, very similar process in Canada, where we have the National Research Council, which publishes the National Building Code of Canada. And, most of the architects on the call probably know this already. And we have each province that kind of like either publishes their own provincial building code, like Ontario does, for example, or British Columbia does, which are usually based on the, National Building Code, but they are so modified that it doesn't make sense to have them, as kind of like referencing back the National Building Code, or they just adopt the National Building Code as is. So that's like happens like at the provincial level, and then you have like standard writing associations like CSA or CGSB, which is almost defunct now, that publishes standards that are referenced by those building codes. And the same way ASTM has standards that are very specific to seismic requirements and for ceilings. CSA has a great standard, which we're going to talk about, that references basically what we call in Canada operational and functional components, which are essentially the non-structural components of the building. Okay, so seismic. Sorry, I know there are a lot of numbers here, but I'm not trying to scare you. One of the big questions that I often get asked by, either an architect or a building owner is, okay, well, how do I know, or when do I know that I need to have, some kind of like seismic restraints, or I need to kind of like take care of the non-structural components in my building? Because historically, it's like, okay, well, it's seismic, it's earthquake stuff. Don't worry about it. My structural engineer is going to deal with it, right? Like that has kind of like generally been the approach to these things, until, as Isabel has said, like, we realize that like, hey, if you have the ceiling falling on you, it's not such a good thing. Or if you have, ceiling mounted equipment that fails during a seismic event, that's not a good thing. So there's a clause in the NBC, and you will have a recording of this presentation, and it's clause 418, 4.1.8.18, sentence 2. And it basically says that for buildings other than post-disaster buildings, and a post-disaster building is essentially any kind of essential facility. So the first thing we think about is hospitals, right? Like, so, we want hospitals to remain available if there's going to be a lot of sick people, right? Like if your hospital is down, then like, you have bigger problems. So these types of buildings have to basically be designed above and beyond the kind of like regular requirements of the code. So for buildings other than those type of buildings, seismically isolated buildings, or buildings with supplemental energy dissipation systems, where this value, i.e. FASA 0.2, and don't worry about the numbers, is less than 0.35, then you do not need to consider seismic restraints. So what that essentially means is that if you're over this threshold, and this is like literally just a question that you can ask your structural engineer, usually on your structural drawings, like on the structural drawings, they will have the values for these different factors. You can multiply them yourself, or you can just ask your engineer, is this value over 0.35? If it's not, and you're not a post-disaster or seismic isolated or a building with supplemental energy dissipation systems, don't worry about it. You're good. If it is, then you have to consider seismic restraints. What that implies is that if you're a post-disaster building, automatically by the NBC requirements, you have to provide seismic restraints. And that's a new thing that they've added in the NBC 2015. It wasn't previously there. So that actually makes things a little bit simpler. So you just know that, if I'm a hospital, if I'm a data center that's considered post-disaster, if I'm a police station, I better provide those seismic restraints, and I better start the conversation. So we're not really here to tell you necessarily what to do. I mean, Isabel is going to get into like the nitty gritty of like how to kind of like install and brace some of these ceilings. But really what we're hoping to do with this presentation is at least start the conversation. Because, I know from experience, and unfortunately experience can be painful, where the contractor has charged a huge extra because the code required us to provide seismic restraints, and it was something that was missed by our consulting team. So I'm not going to say the project, I'm not going to say the architect, I'm not going to say anything like that, but that can be a very painful experience. So generally, if you're a post-disaster building, just automatically think seismic restraint. So what are these non-structural components in buildings? The Canadian standard calls them operational and functional components because, we're fancy in Canada. So, that can be a lot of things. And as Isabel was saying, so that goes from anything like your suspended ceiling assemblies, sprinkler systems, furniture, because that could move and topple over during a seismic event. Or on your roof, like, you have your mechanical equipment on the roof, parapets, cladding on the exterior of the building, raised access floors. So you can start thinking that like, oh my gosh, like there's so much, right? Like, do I need to literally just brace everything? Do elements such as acoustic clouds also require seismic restraints? So Leah, I'm going to go ahead and say if there are ceilings suspended, there's a great list of items that has been published by the Ottawa Contractors Association that I can share after the presentation. So I will say yes, if they're suspended from the ceiling, I would say treat them as like, you know, restrain them if you need to, right? Like, because it might be that you don't need to because of the type of building that you're doing. So what exactly does the code require you to restrain? So there's this table in the National Building Code, and it's replicated in a lot of provincial building codes as well. And this is called the elements of the structure and the non-structural components and equipment. So this is the list basically that the code requires you to restrain. So as I was saying, like, you know, we can kind of like start going on and on and on and on and basically start restraining everything. Um, but I think that there has to be a balance between, you know, how much is it going to cost and what are the risks, right? So that's something that has to be decided on a project by project basis. But you know, codes are jurisdiction, so as a minimum to be, you know, for the building to pass, like, you know, basic legal requirements. And again, this is the bare minimum. This is bare life safety minimum. You can go above and beyond that. If you need non restraints, these are the items. And the good thing about this list is that it's actually organized in a logical way. So the first 6 items are all structural items, you will notice. So exterior and interior walls, cantilever parapets, those are all kind of like exterior or kind of like things that would require like structural design or whatnot. Items 11 and on are all mechanical or electrical type items. And the mechanical engineers have like usually pretty good sections on seismic restraints. 7 to 10 is really what you need to worry about as an architect or a designer. So these are kind of like the components of the building that would be under the purview of the architect or the designer. So suspended ceilings, light fixtures, and other attachments to ceilings with independent vertical support, masonry veneer connections, access floors, masonry or concrete fences more than 1.8 meters tall. So this is essentially what the code needs as a very minimum. But again, this is the bare minimum. I know that on a lot of healthcare projects that I do, you know, things like medical equipment, like head walls or patient bed service units, we typically ask that, like, you know, they're installed in a way that will restrain them in an event of a earthquake, because, you know, you kind of have to think about it, like, you know, if the patient is on some kind of like life support drug and there was an earthquake and then that got disconnected, and you know, they, like, you know, that could affect them, right? So you kind of have to think above and beyond the minimum requirements of the code. But basically this is what the code requires, and this is found in table 41.8.18 in the National Building Code. So that's what I kind of like wanted to talk about. You know, I didn't want to confuse anybody, but like, I think that it's important to, you know, make the distinction of like, you know, when do I actually need this? And, you know, not necessarily solve the problem, but definitely start the conversation with the structural engineer if needed.
Yeah, and there was a question in the chat room from Leah about acoustic clouds. Yes, they would require restraint. So that's why sometimes it becomes a beautiful element of design that becomes extremely ugly because all these additional restraint, depending on the region and the type of building and occupancy, it could become something that all you see is a bunch of wires and posts, and it's just not worth it. So those are the things to consider. We like clouds, but sometimes clouds don't like seismic. It's just just reality. So back into standards and the more nitty gritty, if you will. The standard C635 is about manufacturing, testing. What is it that you have as a T-bar? What is it that you have as a lay-in panel? and how, as a manufacturing company, you should meet specific requirements depending on where it's going to be used. So we're talking here acoustical tile, but as a lay-in panel, you can also include a metal pan. So it's an aluminum or a steel square rectangle that would lay in the suspension instead of a acoustical tile. And then that goes down the road of anything metallic that is laying in as a suspension. So it could be an open plenum concept, not just solid piece of metal. So anything that is using a T-bar that could be considered a lay-in panel will be included in this. The suspension is really what holds things. So I'm still in the C635. I'm sorry. So I'm just going to add a couple of things. So 635 is about manufacturing. So what it tells you also is to classify what they call the duty, which is the amount of strength that your suspension should have. So there are three things: a light, a standard, and a heavy duty classification. So a light duty would be something that would be all aluminum and then would have some weaknesses to it, and there could be some limitations in terms of seismic installation pertaining to that. Something that would be on the regular intermediate duty, as we call it, as the classification would identify it, you would have tests such as the pull strength that would be considered in terms of if you're going to click in, as in the picture, you cross these to the main, and then you would pull on them, how these little connectors would resist to that pull. And that's part and parcel of what that seismic action would do to your suspension. And then you have the heavy duty, which now says very specifically how much more meat that suspension will have. So the main runner would be heavier, more metal to it. The pull strength would be a greater number. And those are specific things that you decide to adhere to and meet as a specification when you manufacture these things. That's the basic and the very, very simplistic way of looking at that standard. But it's a critical standard. That's why it's listed in every spec.
Yep.
The next one is C636. Now that's about installing it. What is it that you do with it? So again, it's a standard procedure in terms of what the expectations are and what is it that you would like to do depending on the height of your substrate above. What is it that you can or cannot do for hangers, how to do it, how and where your ceiling fixtures could connect to that suspension or not, with a separate or additional safety feature for seismic, for instance. You have additional safety chains that are added to it. There are great documents from associations of contractors that have been developed over time that give you very quick and dirty ways of looking at it. And there's also associations of contractors that give training for contractors that are doing interior finishing to how to do these things, how to recognize the system from one company to the next and what's the best practice about all that. Again, something that is worth always listing in specification. Not that anybody knows that or recognizes it, but Just and I, we know that, we see that, you know, and there's a lot of worth into that standard if we need to dig into it. And then we have the STM that is specific to the seismic activity. So this will go into the detail of what is it that you have as a need to do for securing your ceiling, depending on the risk level of seismic activity. And again, depending on that level, what are the different connection strength and what are the limitations that you may have. It's a lot of times kind of related to thinking about I always say what my grandfather would have done way back when he didn't know any better, but he had that good common sense about there's a basic element that needs to be addressed. So now we have categories, we have numbers, we have classifications, but a standard is about a consensus, a best practice without going into one element versus another, but trying to convey as much information as possible. So they get to be updated every so often. Okay. The Canadian codes had for the longest time a numerical systems for classifying seismic risks, 1, 2, 3, 4, 5, 6. I think it went all the way to 9. Things have changed and evolved a little bit over time. And what we have seen is that a lot of times because manufacturing companies have documentation that are based and produced in the States, with reference to what we see now, we have a lot of times engineering in Canada that it will connect the dots from a Canadian building code to what a manufacturing company will provide as data. So I will go about these classifications, but you will see where like I said, my grandfather's common sense get into play and into all that. So you have what they call seismic design categories, which is from A to F. But A and B are not very often addressed because they're considered for a low risk of earthquake damage. If you happen to have this popping up because an engineer has flagged something, it could be because of very specific things. It could be because of the type of soil, or maybe a snow load that creates maybe in some areas something of a flag. So then you would have maybe specific documentation in regards to the actual geology or maybe the environmental risk that could be creating additional damage if the earth was going to shake a little bit. Sometimes the shake is not a real shake. You have a sense, oh, I think I felt something. Or a few years back in Toronto, I actually saw in my backyard the ground going like a little wave. And I thought, oh boy, I need coffee. What's going on here? And it was actually reported in the news that we had a little earthquake, and downtown, some of the buildings, people at the top could feel it. So they will happen everywhere. So A and B could be because there's a need to flag something that way. Where we really start talking seismic installation, where the contractor will add that additional fee because he knows he's going to have extra labor, is when you go to a C category, and then the D, E, F that are grouped together because they are the ones with the strong risk. So D, E, F is a category of its own, and then C is a category of its own.
Okay. Isabel, can I add one thing very quickly?
Sure.
Yeah, there's one thing that I forgot to note when I was speaking, is that there are three main things that affect your kind of like your seismic level or seismic level of risk. So there's the type of building, and I think I spoke about that a lot, but I kind of like got a little bit carried away. So there's a type of building. So are you doing some kind of warehouse that nobody's ever going to visit? Or are you doing like an important hospital or a police station or a fire hall, right? So that will determine like what level of mitigation you need. There's a type of soil, right? So if you're building on like very strong soil, like bedrock, that might not affect how much the building shakes, versus if you're building on something like clay or something like that. And then there is the location. So as I think we've covered all these things, but like I kind of like want to put them together. So if you are in Vancouver, even if you're doing like potentially a warehouse in Vancouver, you might still need seismic bracing because there's just like more susceptibility of the ground shaking in that location than there would be over here in Toronto, for example. So those are the three things that affect seismic restraint. So that's why it's not always so straightforward to just be like, oh, don't worry, we're just in Toronto, we'll be fine. It could be a hospital in Toronto, it could be a data center in Toronto, or it could be a warehouse in California, right? Like, so you kind of like always have to keep that at the back of your mind and ask the question. Yeah, that's it.
Okay, no, that's good. Thank you. So now we look into the actual suspension. What is it that it's going to need to do in order to react a little bit better as a ceiling to some kind of a movement of the building? So when we talk category C, we know it's going to probably wave back and forth and move enough to rattle things on the shelf, and then maybe that your ceiling will start to resist. If it's too connected to the walls, it will resist movement, and then the energy has to spend somewhere as to release. That's where you get the breakage and the thing that tear apart. So what we say with the category C as a medium risk is that let the ceiling float. So the idea is to minimize the risk of that buildup of energy into the ceiling to rip it apart. But at the same time, you still need that ceiling to stick together so it doesn't become a spaghetti. So we are able to still use materials that are the average, the intermediate duty, so it's not expensive. You still use your standard wall angles. What you do is that you will make sure that you don't have any screws holding anything tied to the wall. So if you think about a very simplistic room that has 4 walls. So the 4 walls are what you call not attached. So the ceiling is completely disconnected from any hard connections to the walls. It has the opportunity to move a little bit on that wall angle, but you still want to have some kind of a structure to this, so the 2x2, the 2x4, to give an example, remain 2x2, 2x4 rigid lines to hold the tiles in place. So that's where, for instance, the spacer bar get to be used up. So they are like a folded V piece. They come in standard dimensions, and at the very ends of them, they have a notch created. So it just sits on top of the T-bar. So it holds it. It's like a bracing, but a very generic one. It can be handmade if you have nothing available to you. It's been around for a long time, and it creates that security that the T-bars, the distance will remain. So that helps creating enough flexibility, yet some rigidity to that ceiling. So if there's a shake of the building, the ceiling will move and lose that energy by moving a little bit without falling. And because we're talking seismic, the light fixtures that would be resting on the T-bar cannot be solely resting on the T-bar. They have an independent connection. It's not just the wire. It has to be an additional support. When you get to the DEF, where things are going to shake left, right, up and down at a very higher speed and higher strength, the connections need to change. So the testing in place will say that the manufacturing companies have to prove that their system work with very specific items. So your main runners become heavy duty, so they have more weight to them, and the pull strength, the connections have to be a minimum of 180 pounds. So all that connected, and you pull on it, it should resist to up to 180 pounds. These numbers have been there for a long time. Every manufacturing companies that exist in the marketplace that make those things will have these tests. All of a sudden, though, because it shakes and moves a little bit more, we need to do additional things. So that wall angle becomes a very ugly 2-inch wall angle. So it is, if you were going to look up, you would see at the edge of the wall a large piece of metal, not your standard little, very elegant little wall angle. So this, again, is the standard practice. I don't have anything specific in my hands. I can deal with things from, things that exist, been around for a long, long time, and it's recognized. Any building inspector would recognize as being a very large wall angle doing what it's supposed to be doing. So now also what we need to worry about is that of these 4 walls, 2 of them will be unattached, but 2 will be attached. And again, this is to control that energy. So if you look at your square, they are adjacent walls that will be attached, and the opposite ones will be, let's say, adjacent and unattached. So you can see now that you're forcing to control that energy, that movement into a specific direction, because again, that building is going to move left, right, up and down, and not necessarily in the right order. So you're trying to control that energy so the ceiling can move, but has some rigidity to it, again, for preventing a failure and a fall, if you will. So there are specific things that need to be done, and then without going into too much of a nitty-gritty, the connection is a pop rivet, like a screw, and then you have your hanger wires that need to be a bit of an angle to create, again, a sense of elasticity into the system. And then you get to the ugly stuff. So this is where your clouds don't look good, because you have to think about this energy that's going to go up and down. So you need some kind of a post, the different things that can be used. A steel stud can be your post. And then you have your 45 degrees bracing. So these things, for instance, would become very visible. And I know that for a fact because we did that at our company. And we did a showroom and we did something with all that bracing on a cloud. And there's only so much you can do to hide this. At some point it's in your face. So it's this is the negative side of things. When it's wall-to-wall ceilings, you don't see that. Also, with what happens here is that because it becomes such a high energy, so you have to think about breaking it. And yet another manner that and control that is by creating an expansion joint, if you will. So now you have to say, okay, there's so much square feet to my ceiling. I have to give it some breaks. So you have smaller pieces of ceiling moving because the whole thing becomes this gigantic tsunami of energy that comes into your ceiling. So you're trying to control that. You break it down into smaller pieces. Next. So that's where at some point there's some rules in terms of the square footage. There's a, okay, I'm trying to think of the word in English. There's a scale, not a scale, but a measurement that you say from one part. So 25% of your ceiling versus 75% of your ceiling need to be calculated in such a way that's not a long, narrow alley of two tiles going for, like a mile long. You have to break it down in terms more squarish dimensions.
Mm-hmm.
And then it's a ratio. Thank you. All of a sudden the word comes back to me. It's a ratio. So there's a ratio to 1:4 that you need to address in terms of very large scale ceilings. And again, a data center would be an example where you would have a very large ceiling that is uninterrupted. So my grandfather back in the day would say, okay, I understand I need to create a break and I don't have fancy things with me. So I'm going to cut through the main channel or the crusty, depending on where that line has to fall in terms of expansion joint. And then I will try to make it pretty because if you look up and you have a big break, what is it you're going to see? So you cap it and then you have a piece of metal of some sort at the top that is actually closing that gap. So visually it's not as bad. And also is the piece of metal that will bend during that big, huge movement and shaking of the ceiling. So it will be absorbing that energy and hopefully be enough that the whole ceiling is not going to collapse. So those are basic things. So anybody that has no specific clips and funky little accessories from a manufacturing company can come up with a very decent meeting standard layout. So the alternative seismic solution is what manufacturing companies will propose and will test and will publish as options towards all that stuff we were just talking about. So for instance, you will have through a third-party testing, very specific clips that will be promoted to be used as part and parcel of what a manufacturing company will have. So everybody in the marketplace has a report of that nature. So again, we see now that the ASCE, which is the civil engineer of this in the States that are part and parcel of this testing, you get that information laid out and then you go to a company like Intertech, for instance, to actually have a test in a laboratory. And then you can get published then your results. So the results are basically up to failure data, right? So the tests are always all the way to failure point. So you know with these documents what are the strengths and the limitations. So in terms of the span that you are allowed to have in between specific T-bars in order to meet those requirements that are in the seismic standards, for instance. So it's all coming together, if you will, at some point. And this is an example of that shaker table that would be used for testing. So these facilities will test a concrete slab as much as a steel piece for a bridge, as much as an acoustical ceiling with a T-bar. These machineries are very high-tech and very, very powerful. I was told that they do not let people touch the machine while it's shaking because they say it would literally liquefy your insides. because of the strength of the machinery and the shaking level, the vibration that it creates. So these testings are very labor intensive, and usually as a manufacturing company, when your ticket is up for spending time there, you're easily 2 weeks at a time doing tests. Doesn't come around very often because many people are lining up for tests, and when you're there, you want to maximize the money you spend. So you test the heck out of everything that you can. Okay. Oh, we're slow here. We're gonna catch up. Okay, I see the time. So why would you bother with all that? You're gonna say, well, the heck with that. You might as well not put a ceiling if I'm gonna go through all that. Well, the thing is that ceiling is acoustic first and foremost, so you may want to consider that you want to keep your acoustic. You spend a ton of money in terms of beautiful design, so maybe your ceiling is part of that design. It's a plane, right? It's another wall, if you will, so you want to be part of it. And when you look at all these different aspects, and you've made that consideration that you will have an acoustical ceiling, if you go with the alternative solutions that are proposed by manufacturing companies, you have some cost savings because it's like best practice. This is my clip. This is what it's going to do. This is how you can install it. It kind of simplifies instead of the guessing what we saw earlier with pieces of metal that you're going to bend because you have nothing available to you. So a clip would be that connector for the wall, the perimeter wall. It's something that everybody has. It's a great way to easily install a suspension ceiling at the wall, whether you need to have 2 walls attached or 4 walls detached. The clip allows for all these possibilities, allows for that movement. It's resistant enough that it holds the T-bar. It's clipped to the wall angle and to the T-bar, so effectively it should not move in a category C and should eliminate the what were you going to call that? The spacer bar that we saw earlier. The spacer bar and the clip, they both have advantages and disadvantages. When you think about your ceiling tile, they are in the way a little bit. So you have to plan a little bit for that. That these pieces may make it a little bit slower when it's time to install the acoustical tile itself. Okay. And if you go to your DEF, which is the level of higher risk of seismic activity, the idea again is that you need that connection to the wall. You need that spacing for movement. The difference being that the attached wall, your clip would have an actual pop rivet. It would be screwed in, and it would give you a chance to control things. And it also has the advantage of being tested and approved for a standard wall angle. You don't need to have your 2-inch wall angle. So it's nicer when you look up.
Yeah, and the funny thing about that, just very quickly, I know we're over time, but I actually did a hospital in Vancouver, and I think this is before all these kind of like clips were very popular. So we had to do the wall angle, but the interior designer was very, very disappointed because she was like, well, there's this huge 2-inch angle everywhere, and I can't just I'm always looking at it. So that was interesting to see, and we wish we had those solutions when we were doing that hospital.
Yeah, you can imagine in a hospital, a lot of small rooms still need to be addressed. So you have an awful lot of that white piece of metal in your face all the time. So yeah, I can imagine.
Yeah, she was not happy.
Yeah. And then for that expansion joint, there's separation clips that exist. Again, manufacturing companies go and test these things. Everybody has their own way of doing it. They are very different from one company to the next, but they all give you the opportunity to cut through the main or the cross T, depending where that line should fall, and give you a chance to adjust things and cover that gap and give that movement that you need. The best way to know whether or not you have an expansion joint is when you look, if you see a little capping that covers your T-bar, and each T-bar has that at the same place, and it creates that little line that all of a sudden you visualize, and you know it's the expansion joint that's hiding behind that little capping. Okay. Where are we? Okay. And at the end of the day, who will enforce all that? Depending on the province, you will have more or less of these building inspectors. In Quebec, apparently there's less of them. In Ontario, we have a lot of them. But they are the ones that know the building code. It will be asking questions about that clip and that expansion joint. And what is it that you have there? Why did you pick this one? They will be the one asking questions for documentation. So don't hesitate to ask manufacturing companies for that. Okay. Quick summary, because we said a lot of things. So 75% of the building is where you will have to think about what is it that's going to fall on me or towards me or below me. What is it that we have for seismic standards? We have a lot. They've been in place for a long time. They do an excellent job at creating quality material. What do I need to worry about? Where is it built? What kind of building? What kind of occupancy? So sometimes you have a red flag. It could be one day you're doing a high school, and the high school is a post-disaster. Not just hospital and fire halls, but high school. High schools have large gyms. They have shower rooms. They have cafeterias. They're great places to relocate people. Okay. Do we have another slide? I think we do have a couple. Almost done here. Steven says he had to go. Bye, Steven. Okay, documentation of all this. If I can pinpoint you to the Ceiling and Interior Systems Construction Association, the last one to the right, the CISCA, great document for you for reviewing the nitty-gritty. Next. I think we're at the end. Just the Rockfon products. So that's very, very quick. By Kelly. Kelly had to go too. So we do acoustical ceiling tiles, very different than the rest of in the marketplace. Lots and lots of sound absorption, great finishes. Go check the website. We have on the next slide the suspension system. We are very, very versed into that because we have to deal with that a lot. And the seismic is no stranger. So 15, 16, and 16, lots of different types and looks with those testing. And then the last little bit is metal ceilings. So metal ceilings would also have some specific products that are perfect for seismic installation. So those are the things to look at. I'm done. I don't know if there are any questions. If you want to continue, I'm okay for a few more minutes. It's up to you guys.
I actually have a question, Isabel.
Yep.
The seismic struts, if we use your clip systems, does that mean that we no longer need the post and the struts?
No, they will always be needed in the highest risk categories. You have to have that.
Okay, yeah. Perfect. That's what I wanted to know. Are there any questions? No?
I mean, the question could come tomorrow, next week.
Yeah, absolutely.
This is when sometimes it hits you in the head. You go, oh my God, I just went through that. Yes, I have a question.
Somebody's typing.
Oh, yeah. Okay. So Leah had a question that we partially answered. So go for it, Leah.
Yes, they come up. And I'm sure everybody has my email, so feel free to just email me directly. I can pass your questions on to Isabel. But I guess if there are no questions, we're just going to wrap up. And I realize that we're also over time. So I'm sure everybody has somewhere to go, another meeting to attend. So just want to take this opportunity to thank you all for attending. I want to take the opportunity to thank Isabel and Rockfon for presenting with us. This was, great information, I think, but I'm a little bit of a nerd. So I think that the stuff about seismic is always fascinating. And, a lot of people assume that just because they're in a certain zone, they don't need seismic restraints. But I guess if we achieved anything today, I'm just hoping that we would be able to kind of start discussions, or at least kind of jog people so that they can ask questions, and these things can avoid you an expensive extra down the line. So thanks again everyone for participating, and thank you for being for attending these webinars and for supporting Bibliotech. And we will follow up with I wrote some documents that I want to share with the attendees, as well as your certificates. Okay. Thank you so much.
Yeah, thank you.
Okay, bye now.
Bye bye.